Hello everyone and welcome to this lecture on biasing and DC sources. Today we are going to talk first about the separation of DC bias and the signal path. Then we're going to study general rules for biasing, practical implementations of DC voltage and current sources. Then we're going to go to a method for doing biasing step by step. I will show 3 examples of a single-ended and differential stage, and then we are going to touch a very interesting topic that it is how to bias the fully differential stages, and I will show an example on this last one. So we have that we have been working until now with the signal paths that are formed by the small signal models of bias transistors. So the signal path is basically formed by transistors that are nonlinear devices that are operating in a particular operating point, and placing the transistor in that particular operating point requires 4 DC sources, 2 current sources and 2 voltage sources. And these DC sources, what they do is basically they place this transistor in the side operating point, and they also remove these voltage and currents from our calculations and basically from our simulation setups, making it very easy to handle the transistor almost as a black box. So we have at our left that the bias transistor, it is basically equivalent to having a small signal model, and the removal of the offsets, the biasing offsets, make that this voltage here it's equal to 0, and the current is also equal to 0, and then also here the voltage is equal to 0 and the current is equal to 0. So basically these biasing voltage and currents are totally removed, so we can connect any impedance at the input and the output, and then these basically these offsets are totally removed. So then we can basically run every kind of AC simulation, like a noise AC simulation, pulse zero simulation, etc. So at some point we will be happy with our small signal or signal path. We'll be happy with the compensation, and we need to come back and implement these DC current and voltage sources, and that is exactly what biasing is. Biasing consists of implementing these sources, 4 sources per transistor. Now, implementing these sources is not trivial, so we are going to use a very easy method that it is very powerful, and it comes actually with the use of very simple tools that we learn in the basic electric principle circuit. So the first concept is that the only true power supply in our circuit, it is VDD. So at the end of the day we will have only one power supply in most of the cases. There are some exceptions in which there is multiple power supply domains, but typically in an analog circuit, in an analog block, you will end up with one power supply that we will call it VDD. So from the bunch of power supplies, DC power supplies that we have around our transistors, we have to transform all these current and voltage sources until we have only one power supply remaining. And the tools that we're going to use, as mentioned before, they are simple tools that we learned in the electrical principles course. And it is first a Thevenin to Norton transformation, the one that we see here. So we can convert voltage source in series with a resistance to a current source in parallel with a resistance. Then we can also use the following transformation from current source to two current sources. So a current source that go from point B to A, to a current source that go from point B to C and from C to A. And the last one that we're going to use is a transformation when a voltage source crosses a node. So it can be pushed in this node and then it appears as several sources in the other side. So those are the basic tools that we are going to use to move DC sources around our circuits, and that it is basically going to be extremely powerful. And these are basically exactly the same tools that we use for input noise calculations. So as I mentioned before, we have four sources in a transistor, and yeah, we can simplify our problem assuming that we have a DC feedback loop that can control the sources at the input. Okay, so in that case, if we have this loop, we can control the current source at the input here and the voltage source at the input here. Now, very often we already have this DC loop in our circuit. In particular, if we are designing a negative feedback amplifier, there is a loop already in the design. So very often we can reuse this feedback in order to control these input sources. And then I think you already saw this circuit before. It is exactly the same setup that we use in order to find the VGS voltage when we do the self-biased transistor. So it is just a negative feedback loop that it is finding the VGS. So this is not really something new. We have already been using a few lectures before, but the same concept comes back to us. So some general rules for biasing. So we have our transistor, the output curves of for our transistor look like the plot that we have in the right. So if we have our operating point, for instance, here, or operating point Q, here, the transistor, we place this transistor well in saturation, and we basically decide in which VDS the transistor is going to work, and then we take enough margins so that this VDS can go up and down depending on the linearity requirements. We can see from here that the variations on VDS can be tolerated as long as the linearity the linearity requirements are not violated. So I can move the operating point here, or I can move the operating point here, and this transistor will still be in the saturation region. And then if the signal swings are large enough, the linearity will not be affected. So the voltage that I cannot change very easily, it is the VGS, because VGS will move these curves up and down and will change the current. But so VGS, it is a voltage that must be very well defined. But VDS, on the other hand, I can tolerate rather large variations of VDS as long as that linearity is not affected. So we can say that the drain terminal in a MOS transistor can be considered a floating node, and that will be very helpful because sometimes I can just remove a voltage source that it affects mainly VDS in a transistor and let it float. As long as the variation doesn't affect my linearity, I will be fine removing that voltage or current source. So drain terminals in MOS transistor are floating nodes. Now, generally speaking, we need 4 sources, 2 voltage sources and 2 current sources to bias let's say a network including active devices. Now when we concentrate only in NMOS transistor, we have that the only gate current that exists in a MOS transistor, it is the leakage current. And in most of the cases we can disregard this DC current because it is extremely small, and it is only relevant when our amplifier or other circuit that we are designing has extremely high impedance of output impedances, or the feedback it is very high impedance. Then it becomes relevant, this leakage current, but otherwise in most of the cases we can disregard. So since we can disregard it, then we can just remove this current source at the input, and then we only have 3 sources to implement left. Then the circuit for biasing the MOS transistor is the one that we have at the left. We have a similar one for biasing a PMOS transistor on the right. As we can see, only the signs have changed, and now we have the VGS will be VSG, and actually we just have to change the polarity of VDS or VGS to put the transistor in the operating point. Okay, so we have these 2 models. Those are the ones that we're going to use later. So what about passive components? What is the role in biasing? So to start with, the linear components do not need biasing. Yeah, so the resistor, capacitors, and inductors, they are linear, so we don't need to put in a particular operating point. So it is only active components that need to be placed in a specific operating point. Linear components are useful as part of the biasing. We have that the resistors produce voltage drops, so they can work as current sources. For instance, let's see, we have an amplifier, a common source amplifier, and I can put a resistor as a load, and this resistor will let pass a current equal to this voltage resistor divided by the resistance. We call it this resistor load. Okay, so I can load this amplifier with this resistor and use it as basically as a current source. So that this will be the current that passes here. So it can be used as a voltage drop. Sometimes I need to create voltage drops, or it can be used as a current source. Yeah. Capacitors are very useful. They can be used for decoupling 2 nodes, so reduce impedances. Typically are placed in parallel and used for filtering. And the decoupling capacitor, for instance, we have our power net here. We have our ground, and then it might be that our power supply is located very far away from our circuit, and we have some inductive behavior before it comes to our circuit. Then our circuit is going to be located somewhere here. Then we can use the decoupling capacitor to reduce the effect of this inductance. That it is here. So if we have here the decoupling capacitor. So if there is circuits that are dragging, let's see, that are more inductors, and there is another circuit here around. So if there is a lot of activity, for instance, digital activity happening far away, that are changing the currents in this circuits, then the coupling capacitor will hold the voltage. So basically it's going to filter out the digital noise that is happening here. So we use the coupling capacitor as filtering, and I will show some examples later how we do filtering in the Bayesian network using the coupling capacitors. So basically we use as filtering, and we put them in parallel. Then they can also be used as coupling capacitors. They connect two nodes for signaling the information band, and we can probably reuse so our amplifier here. So if we have a load here, okay, we can call it here R1, and I typically cannot connect it directly because they will have a direct DC path from a VDD to ground. So I can probably connect a capacitor here. And as long as the capacitor is large enough so that it doesn't affect the signal bandwidth, then these two nodes will be AC coupled. So that is a coupling capacitor. We can put on the input, or we can put on the output. I can also use them in the feedback, as we will see very soon. I can create voltage controlled voltage sources or current controlled voltage sources. So these capacitors can be also used as a control source. So we will see an example how does it work, because some of these input voltage sources, some of these input voltage sources might be replaced by capacitors connected to the feedback. So we will see an example. I can create a floating node, typically used at the output. So exactly the same examples that I showed before. The placing of the capacitor, leave the drain voltage floating. So it basically create or give the opportunity to create a floating node. Inductors, they are short circuits at DC, so at very low frequencies they are not very useful. They increase the impedance at high frequencies, and then it gives the opportunity to use to bias circuits at high frequencies. And an example of that, it is again, we can take a look at common source amplifier, and very high frequency. I can use this inductor as part of the biasing. So at very high frequencies, these capacitance and these inductors will resonate at the frequency 1 divided by the square root of LC, and then at this frequency we will have at this circuit this circuit behaves like a common source amplifier with a resistance, and this resistance depends on the quality factor. So it will be the series resistance of this inductor. This inductor always has some serial resistance multiplied by around the square of the quality factor. Is 1 plus the quality factor of the inductor. So we can use this as a we can use this circuit as a it does inductor as part of the biasing. For DC, of course, this is almost a short circuit, very small resistance here, but actually this will be for AC. For AC model, we will have a large resistance here. Okay, so that is basically the use of inductor. We can actually also bias the input. We can use a current mirror here. We can probably bias the input with an inductor and then connect this to a source with a coupling capacitor. So inductors are very useful at high frequencies. Something that is going to be the topic of the next course in radio frequency integrated circuit design. But we are not really going to use much inductors here. Okay, so then we have to implement at some point all these voltage sources and current sources, and there are some ways to do this. To implement a voltage source of a particular voltage, let's say the easiest way to do that, it is to use a voltage divider, and then one of the characteristics of a voltage source is to have very low impedance. So we can use a capacitor to the coupling capacitor to reduce the impedance of the node in the frequency of interest. So this is one way of implementing a voltage source. It is not very amenable for integration if the resistors are very large, but it is one way of doing implementing a voltage reference, a voltage source. Another way of implementing a voltage source, it is to use a diode connected transistor. So as we saw, the diode connected transistor has an impedance of around 1/GM, that it is normally very low. So the circuit guarantees that we'll have a low impedance. Instead of a resistor that sets the current, we can use a current source. So we can have this variant. The problem of this kind of connection is that the voltage in a diode grows logarithmically with respect to the current. So large variations of voltage require large currents. So it is not very practical if we need the large voltage drops. So one thing that we can do is to pile up diode connected transistor in order to generate larger voltage drops. We can have a variation also. We can have a diode connected transistor and resistor in series also. Something else that we can do is that we can use a combination of diode connected and triode to put the transistor in triode as here. So this is basically equivalent, just that this transistor has been placed in triode. But typically we will be using something like this in our circuits most of the time, or like this. So for current sources, we have the following alternatives. First, as we studied before, we can convert a voltage to a current using a transconductance amplifier. And in integrated circuit design, typically we designed a very clean voltage reference that it is independent of temperature and voltage and process variations. So this is a band gap reference, so that normally is very stable under different conditions, and then we convert this voltage to a current using the transconductance. So we use this one as a reference current, and then we distribute this very clean reference current around all the analog blocks of our chip. And when this reference is coming, then we can, for instance, copy it using a current mirror, as we see here, the current mirror. And this current mirror has a one output transistor here. We have that the output resistance here, out, is equal to RDS of this transistor. We can call it the transistor M1, RDS1. Very often we need higher impedances, and then we have to resort to the use of cascode, and one of the alternatives is the one that we see here, is a cascode current mirror. And in this case, the output resistance will be equal to, if we call it this M1 and this one M2, then we have already discussed the cascode before, so this will be RDS2 times the loop gain that we have in this configuration. That will be 1 plus 2 GM2 times RDS1. Okay, and this is approximately. So this is much more higher than the one on the left, that's just the current mirror. And the disadvantage of this stage is that we have one BGS here and another BGS here. We call it this 2 and this BGS1, which basically means that the voltage that we have at the output here, the voltage signal swing here, it is quite limited, because this point here will be basically BGS1. It will be limited, this voltage here, to BGS1. So that can be much more higher than the voltage that it is actually required to keep the transistor in saturation. That, as we discussed before, it is just above 100 millivolts in the case of a subthreshold, a transistor placed in a subthreshold, and above BGS minus VT if it is in saturation. So instead of this, what we can do is we can use the circuit on the right here. Has exactly the same output resistance as the cascode. Is a cascode configuration, but we press this voltage VDS1 a little bit down using a resistor here, and then we have the freedom to go down the gate voltage here, so that we go down also the VDS2. In this case it is M2 here and M1. So if we track VDS2 around VDS1, then both currents will be exactly the same, and then that gives me the freedom to go down the overdrive voltage that it is needed in M2. So this is one alternative, but it requires one resistance, and then we have that the resistance and transistors can have different variations, process variations. So alternative that it is also possible is to use the following. So instead of using a resistor, I can use a transistor here. So, but the principle is exactly the same. So I bias this transistor at a particular voltage, and then I press, if I call this M2 and this one M1, I press the voltage of the drain of M2 close to the voltage that is necessary to keep the transistor in saturation. As I mentioned before, above for thermal voltages above 110 millivolts in subthreshold low, or to the voltage that I need to keep in saturation the transistor when it is in strong inversion. And then I use the same voltage to bias a transistor in the cascode here. So basically I keep these two voltages around the same. And this will allow me to have a wide swing at the output. Very often this is what we will be using. So there is in very few cases when I will probably use the alternative here. So this the disadvantage of this one is that you need to generate another voltage here. But otherwise this will allow much higher voltage swing at the output, which is valuable in low power applications. Okay, so after having seen how we will implement the DC voltage and current sources, then we will have to check exactly what are the recommended biasing steps. So first we have to replace the small signal models for biasing transistors. So we use small signal models to do compensation and by loop gain calculations, and so at some point we will be happy with the results with our small signal models, and then we have to replace these small signal models for bias transistors. So, and then we can identify DC feedback loops that are already present in the signal path, unless we have capacitors in the feedback. Then we will almost always have some DC feedback loop already present by design, because we are designing negative feedback amplifiers. So there will be a feedback loop that maybe we can reuse. Then we will start reducing all these DC sources by using the tools that we studied before. When we reduce all of these sources, we will see what are the requirements for the power supply. So if the maximum power supply, when we reduce the maximum addition of DC power supplies at some node exceeds the available power supply, then I will have to fault some device, change some device type in the signal path from NMOS to PMOS. But I have to check if this is necessary. There are other considerations of practicality of implementing the feedback that also might force me to change a device from NMOS to PMOS. Then I can identify the floating nodes that cannot be tolerated. There is a number of floating nodes, for instance, those that are controlling gate to source voltages. There are some that might not be possible to change. And then I might need to implement DC feedback loop. For instance, if I cannot use the DC feedback loop already present in the design. Some control sources I replace by capacitors. Finally, when I arrive to this point, then I can do the transistor implementation of the DC voltage and current sources. Okay, so this is basically the method that we are going to use for biasing. So yeah, so we will have several examples so you can see how the method works, and we will start with the single stage transimpedance amplifier, and we have here the signal path, and so we are going to go step by step until we have a complete bias circuit.